So now let's, in the previous class we had introduced statistics, right, and statistical inference. And the idea was it's about estimating from data or learning from data, right? The idea is there are some unknown parameters and we want to estimate from data, and that was more specifically parametric detection and estimation. And I said in the class we'll focus on that here, and then in some advanced maybe lectures we can do the non-parametric aspect. But like the main setup was there's some unknown parameter theta, right? And then we have the data represented by y, right? So this is unknown, and this is observed. And the two are related through a model, right? And the model is nothing but the distribution of the data under these unknown parameters. So we represent it through this distribution f. And when we say we are modeling, in a way we are making choices of what are appropriate distributions, right? So in many of the applications, modeling itself could be a huge part of design of the problem, right? I mean, once you have the model, you can ask for solutions, but the question of what is the appropriate model can sometimes be the bulk of practical design. And in this class, we are not covering a lot of that, but keep that in mind that this can be a red herring in many settings, right? Like, how do we choose this? And this is where deep learning has been effective because it's non-parametric. It can approximate arbitrary functions given enough capacity. So people have tended to prefer that for complex data because you don't have to worry about what's an appropriate model. But in so many settings where enough data is not available, or you have all these constraints like safety and other requirements, having information about the model or what's the right model can be very useful, right? And even in deep learning, when you're choosing a neural network, it's not completely arbitrary, right? You're deciding, there should be convolution when there is images, or there should be max pooling because I'm reducing the dimension, or the resolution, right? So all this, you're making choices. So in a way, there's always a lot of thinking that goes into model design, architecture design, right? But we will not be covering a lot of that in this course because that is highly application dependent, and it's more of an art rather than science at this point. Maybe one day it'll change, but it is still very much based on intuitions, and heavy methods like architecture search tend to be very expensive and not practical, right? So that's still very much an open problem. So keep this in mind. From here on, I won't be addressing this aspect, right? How do we choose this? Why is this an appropriate model? We'll take it as given for the rest of this course, at least rest of the course on statistical inference. But any thoughts or comments before we move on? Because the modeling is an important issue. So if you've had experiences, where you probably made a bad model choice, or you found something surprising, I'm curious to hear before we move to the aspect of statistical inference. Because in the first class I heard several stories of the use of machine learning in different domains, right? So do any of you have thoughts you want to share with the class on how you chose the model, or was there something that was surprising or not intuitive?
I think some of the line of work that follows like a paper like the deep image prior, I'm not sure if you saw that, where it's like commenting on how for CNN to like reconstruct an image, when you do it in like the lowest energy way, it actually can like help like denoise it, for example. And so the inductive bias of the model is like the model choice can actually affect very much like how data is, how do I put it? Like if you choose a good model, right, it can really fit the data well without like any training. Is kind of the sense.
I guess what you're going after is also robustness.
Yeah.
Right? Like having a good model can also make it robust. I mean, in this case, right, even if there's noisy data, it can denoise it, right? So good choice of model isn't just a solution in the clean case, but also in the more challenging case where there's noisy data, right? And that's why it's very important to stress test the model, right? Like not just look at the data you have and what test accuracy it's providing, but in terms of, especially if you want to go beyond that to some real world applications, you want to ask, what other kinds of unusual cases could happen here or failure modes can occur. You want to explore that. And that's more an art today, right? But maybe one day we can turn the testing aspect also into science. But the general rule of thumb is good model choice leads to a lot more robustness than a model that may still appear to fit the data, but if it's a poor modeling choice, it's not robust. And we'll address some of the robustness as well in statistical inference in the coming lectures. But that's an important aspect of modeling. Any others? What are some modeling choices you've made in different projects? Or you've seen online, or you've seen articles about that? Okay, we'll move on, but in future I do want participation from the class. So, don't hesitate to share your thoughts, because I want this to be also very much interactive. So yeah, keep in mind, and again, if you have other thoughts, feel free to even share them on Piezo, right? So again, this doesn't have to be limited to the class. So that's about the model, right? That's where we start. And for statistical inference, the idea is once we are given this, what do we do, right? And that's where we have the inference part. And what the inference part does is, come up with a procedure to use the data and come up with an estimate of the underlying parameters. Right? And we'll call this a detector or an estimator depending on which scenario we are dealing with. Right, so this part is the modeling, right, whereas this part is the statistical inference part. Is that clear? And in this class, we'll be going in depth into statistical inference, but in a practical application, you'd have to deal with everything, right? You can't ignore any pieces of this. Okay, and then last lecture, we said there are two important categories within inference, that is detection and estimation. And the detection was where there are finite set of realizations of theta, right? So this theta takes only finite number of values, whereas in this case it is continuous. And we also said detection, another name is hypothesis testing, because you're testing over a finite set of hypotheses. Right, so, and in this class we'll be focusing on detection. Another categorization we did was Bayesian versus frequentist. right? So we went into detail last class, but just to recall here, the idea was in frequentist setting, theta is fixed, whereas in the Bayesian setting, theta has a prior, right? It's drawn from some prior distribution. And in the Bayesian setting, we compute the posterior, right? The posterior is the probability of theta given the data, right? Given the observed data. Whereas in the frequentist estimation, all we can ask about is, come up with an estimate of theta. Right? Here you have the distribution of theta conditioned on the observed data, whereas here you're coming up with a point estimate of theta. Of course, given this posterior distribution of theta, you can further ask for different kinds of estimates of theta. Right? But you have the posterior, and that's the key aspect of Bayesian inference. Okay, so that's what we looked at in the previous class, and the last thing we did, I guess the most significant portion of the class was the sufficient statistic. And I think this, to me, this is a very important notion, because when you collect all kinds of data in practice, that may seem like large data sets, right? But the question of how useful is the data for your specific task is an important thing to ask. It's not just the volume of data that matters, right? It's the usefulness, and sufficient statistic gives you a way to say how much the data can be reduced, right? What is the dimensionality reduction you can have for the data? And the way we think of this is through the notion that if you reduce the dimension of data, is the information for estimating theta still preserved or not? Right? If you have no loss in information that corresponds to predicting or estimating theta, then it's a sufficient statistic. Right? So, it's sufficient, right? So that's in the name itself. And then we said mathematically how it's defined is in terms of conditional distribution. What was the conditional distribution we used for the definition? Do you recall?
Like y given ty?
Right.
Like t1.
Right. So ty is said to be a sufficient statistic if you condition on ty and look at the distribution of y, and what does it satisfy? What property does it have?
It's independent of theta.
Right. It's independent of theta. Which is the same as saying that you have no additional information in this conditional distribution about theta, right? Because there is nothing revealing about theta through this conditional distribution. And once you compute T of y, the natural thing that's left is the conditional distribution, right? That's where you look at what is the additional information present through this conditional distribution. So anyone have questions, comments about this? Right? Because this notion of thinking about informativeness through conditional distribution is an important one. Right? So this is the intuitive definition, but the one we argued was much more useful in practice to evaluate sufficient statistic was the factorization form. That was the Nyman-Fisher factorization, and there we said the factorization form is for the model distribution. We take the model distribution and it should factorize into two components. Right? One component that depends on theta should only involve the sufficient statistic. And anything else that's left, the component that is a factor that's left is only dependent on y and not on theta. Right, so if you can factorize the distribution into this form, you've got yourself a sufficient statistic. And we looked at the example of Gaussian distribution with unknown mean and variance. And if you had many IID draws from the distribution, we said what you really want is only the empirical mean and the empirical variance. So if you have the first two empirical moments, that's all you need to know to estimate the mean and variance. Right? I mean, this is something I'm sure you've done in a previous class or you've thought about it before, but probably you didn't think of it through the lens of sufficient statistic. Right? So you just need to compute these summary statistics. In the case of this Gaussian distribution, it's only the first two empirical moments you need to compute. Right? And we also derived that through the factorization form. If you wrote down the distribution for IID draws of the Gaussian, we saw it naturally corresponds to this form where only the empirical mean and the variance show up. Right? So you can see that through the factorization form. And the assignments that are given out, or the assignment that has been given out, tests you on these aspects, right? So for different distributions, how do you compute this? How do you reason about sufficient statistic? So again, I hope that helps you further solidify this concept. Any questions about sufficient statistic? So in the recitation today or no, Thursday? Today. So who's giving the... Yeah, Yuja is giving the recitation today where she'll talk about information bottleneck, which is a generalization of sufficient statistic. I mean, sufficient statistic is, right, nice mathematically, but you can see it can be restrictive, right? Maybe sometimes I'm okay with some loss of information. Maybe I don't want all the information about theta to be preserved if I can get away with a lot more dimensionality reduction. Right, so you want to think of it as a trade-off. I compress it more. Maybe I lose some ability to predict theta better, but on the other hand, I have a compressed form. Right, so that trade-off can be useful, and that's what information bottleneck gives you, that ability. And information bottleneck is an extension in another way, because if you recall, sufficient statistic was a deterministic function. Right, this T of y is a deterministic function. But information bottleneck doesn't have to be. It could be a stochastic function of the data. So these extensions, people have looked at applications to deep learning. I think the jury is still out there whether how useful it is for deep learning, although there are many papers claiming to. So I will ask you to take it with a grain of salt. It's still to be investigated more whether we can use it in a good way with deep learning, but there have been certainly attempts made with the use of information bottleneck. So that's the recitation topic. In a way, this week it's different, right? Last week we did use the recitation to cover the basics. We did probability. So this week it's almost flipped. We are doing the advanced topic of information bottleneck, almost an optional topic because you won't be tested on that. But I think if you're interested in applying these principles to deep learning or some of the latest applications, that can be a useful concept. So I encourage you to attend that at 5 o'clock today. Here, right?
Yes. No, not here.
No?
Nuremberg 105.
105. Yeah. 105 downstairs. Great. So so that's what we'll see later today. And so today we'll move to the, doing both the Bayesian detection as well as frequentist detection, right? So how do we come up with the optimal detectors under different scenarios? And for that, I'll remind you one important concept from this sufficient statistic. So when it was binary hypothesis, do you recall what was the sufficient statistic? So here from now on, we'll use this notation theta naught for null hypothesis, theta 1 for alternate hypothesis. These are the two possible values theta can take. So we'll use this notation. And what was the sufficient statistic for this setup? You had a, yeah. So we had the ratio of the likelihoods, right? And the idea was, and all these keep failing. So the idea was what matters is only the ratio and not the individual values of the likelihoods. And that is intuitive, right? Because what you want is the relative ratio. If you have that the data is highly likely under theta 1, but not that likely in theta 0, then you are very sure that it should be theta 1. On the other hand, if it's equally likely under theta 1 and theta 0, you're not so sure, right? So it's the ratio that matters and not the individual likelihoods. And so we'll be using this form. So this, I'll use the notation L of y to denote this likelihood ratio. And so given that this is the sufficient statistic, in fact, the minimal sufficient statistic, any optimal detector should only use this, right? You wouldn't need to do anything more than this. So all the optimal detection should be based on likelihood ratio, which is great. In fact, it should be of a very particular form, which is threshold detection. Right? For all natural cases, maybe you can come up with some pathological cases, but any natural problem that involves binary hypothesis should be based on a threshold on the likelihood ratio. Right? Because the intuition is if this ratio is larger than some number, then you should declare that it is the do we have more markers that work? I think next time we should just get our own. Yeah. So the idea is, if you've surpassed a threshold, right, you should declare that theta 1 was the underlying hypothesis, right? So theta hat is theta 1, I guess. This is intuitive, right? So you're testing the likelihood ratio against a threshold. So we'll see under different formulations, right, it'll be this identical form of the detector. The only detail is how do I choose this threshold? That depends on the problem setting. So that's a nice setup because you could have many different requirements for your detector, right? But the form of the detection is the same. And even for, if you go from 2 to more hypotheses, the story is more complicated. I don't think I'll do it in this lecture, but I'll give you some pointers in the notes if you want to think more. But the story is not as nice and clean as 2 hypotheses, which we'll limit to in the class, just as a side comment. So any questions here? Right, so keep this in mind for now the rest of the class, that we will think about threshold detection on likelihood ratios. Okay? So given this, I guess now the question is, I talked about Bayesian and frequentist notions. The question of how do I set up these detection problems, right? Because I talked about optimal detector, but then optimal in what way, right? I haven't specified that. There should be a cost function, an objective, and then you can be optimal with respect to that cost function, right? So we have to set that up. And that's what we will do now. So the idea is, we'll define a general cost function. So what that takes in is, what is the detection output? So I'll use capital D for the detection output. If I declare t equals 1, that means I've chosen theta 1, right, for instance. So I have the detection output, and then what is the underlying parameter? Right, so that's my cost function. So for each combination, I have a certain cost, right? If the underlying hypothesis was theta naught, and I output theta 1, there should be a cost to that. I mean, in this formulation, we've also put a cost even if it is the same, even if it's the correct hypothesis, right? This is the general setup. But of course, a special case is where you only count the errors. So meaning this cost function, and if you just equally weight all the errors, right? So any error you make has the same cost, then you can just write it as this indicator function that, right, the two don't match. Right, in this case, you're just kind of going by all the errors. Right, so this is a special case, but in general, you could have uneven costs for different kinds of errors. And we'll shortly see why this general case can be more useful for different formulations. Okay? So once we have the cost, we can ask, what about the minimum cost? Right, so can I just directly think about minimizing this cost? How do I set up the problem? How can I set up the problem of optimal detection given these cost functions? Right, intuitively I want to design a detector that has some minimum cost. How can I set that up?
Expected cost with respect to the observed.
Exactly, right? You want the expectation because this is a random variable, right? So your data is a random realization, and you came up with a detector based on that random data, right? So the cost that is seen, that is realized, it's a random variable. But what you care about is the expectation, right? So that's what we call the risk. So the risk is nothing but the expected cost. And in this setup so far, I'm treating theta to be just a fixed value, right? When we come to Bayesian, we can also average over theta, but so far it's a fixed parameter. And then I'll also use this delta for my detector. A particular strategy that I use for detection, I'll use delta. So this is nothing but if I expand this expectation, right? So I have C, I have delta of Y. So delta of Y is my, gosh. So next time we should just get our own markers. So, right, so I have delta of Y. That is my detector output given Y, right? And then I want to average this over the distribution of data. What is the distribution of data? It's the function f, right? That's the model. Right, so this is my expected cost. Right? So this expected cost, we'll call it the risk. So the risk is, of course, a function of theta, but it's also a function of the detector. And this detector, we've put this as delta. So what kind of function is this delta? Is it deterministic?
I was going to say it's Dirac, or...
No, it's not. Sorry, it's not a Dirac function. I'm abusing the notation. So delta is not the Dirac function. It's just this is the one I've used in the notes. So yeah, don't confuse it for the Dirac function. It's not. It's just some function, right? And if you recall, that's what I used here as well, right? So this is mapping the data back to the underlying parameter. And in the case of detection, you only have a finite set of possibilities, right? It's choosing one of the hypotheses. And in case of binary hypothesis, it can only output 2 values, right? So delta of y is nothing but, right? It can either say 1 or it can say 0, right? Those are the only 2 possibilities. And if it says 1, it means that, right, then the estimated parameter is theta 1, otherwise it means it's theta 0. So does this have to be deterministic? Or can it be stochastic? What do you think? Yeah. No, in general, I'm just saying in general it could be anything, right? I mean, we haven't specified anything. We haven't even specified optimality. I think that's something important to keep in mind, right? You don't have to limit to deterministic detectors. I mean, you can always flip a coin and come up with an answer for what is the underlying parameter. Of course, that would be a trivial answer because if the coin flip has nothing to do with the data, right, it's a valid detector, but it's a bad detector most likely. But keep this in mind that this can be stochastic, right? And so that's why we want to write this in terms of the probability, because delta of y is nothing but probability of choosing some detection value. That's why I wrote capital D as the realization of the detection, right? And then this is given, you observe some data, right? That's what delta of y is. And delta of y equals 1 means this detection output is 1, right? So think of it as a probability distribution, right? And not just a deterministic mapping, right? When I wrote here, you tend to think of this as a deterministic mapping, right? It doesn't have to be. It can be a stochastic mapping. Is that clear? So when you're defining a detection strategy, you think of it in terms of the conditional probability of outputting different detection values conditioned on the data. That's what you want to design, right? You want to design what should these probabilities be, right? What should be the probability this takes value 1? What's the probability this takes value 0? You have to design these probabilities.
Is there an advantage for having a stochastic detector?
That's what we'll address in this class, right? I mean, I guess there's a reason I'm introducing, right? So the question of whether that's useful or not obviously depends on how we set up. Like so far we haven't even discussed what is the detector I want. What should it optimize, right? So the answer would depend. But intuitively, what do you think?
I mean, for outliers, it would probably be nice if you could somehow stochastically change the output. But for most cases, I would like for instance, this specific binary hypothesis, we can think of, because I work with single cells, I could think of either disease cell or good cell. And I would like to have my threshold, I would not like to make stochastic changes in what it outputs as if a cell is diseased or not. So I would like to have a deterministic detector in that case.
So that's a very interesting aspect. So this is, again, something unfortunately we don't address in this class, but the aspect of human interpretability, right? So, and I've heard this again and again from people in other different domains. They don't want stochastic outputs, right? Because they're like, oh my God, can I trust this system? It's going to output something random, then how do I trust this, right? But on the other hand, if there is inherent randomness, a stochastic one could be a lot better. Right? I mean, if there is inherently you're not sure whether it's healthy or not, right? There's so many different factors that lead to unhealthy cells, and you have uncertainty about it. So, in that sense, even if you were to output deterministically, right, you're bound to make errors. But I understand from the cognitive perspective, right, humans tend to be very doubtful about processes that have stochastic outputs. So that's something to keep in mind, right? Because we may not see trust when we deploy these systems. But that's kind of counterintuitive. Like, even though you may feel like, if it's stochastically outputting, this is a bad thing, right? It's only bad if you're having that randomness not related to theta. Of course, if you do random coin flips that are independent of the underlying distribution, that's a bad thing, right? Because you're introducing the extra randomness, and that's going to hurt your accuracy. But on the other hand, if you have correlated randomness, that can be a good thing. Do you agree?
I think so. I mean, when it gets out in the market, I think, like you said, I think it's just about we have a true ground truth of whether a cell is diseased or not.
Yeah.
And if I don't understand why my detector is actually doing what it's doing, then I have more reason to suspect that the randomness is doing something as compared to maybe the algorithm itself, or probably the threshold I'm setting itself.
Yeah. So I guess the key there is the ground truth, right? So you say you have the ground truth, but that ground truth is modulo so many other assumptions, right? So, I mean, even the ground truth is noisy in reality. And I think so unfortunately we won't address in this course, but the question of all the noise that's introduced through annotation or through all the other conjectures people make to arrive at the labels, right? So that's introducing all the noise. So and that's why a stochastic method could be more flexible, because it realizes that there are inconsistencies across different samples, right? So in a way, you could also aim to model all the noises that were introduced during the annotation process, during the process of arriving at what you call the ground truth, right? Because the ground truth may not be the truth, right? And that's, I think, the reason where you would, that's a setting where you would gain by carefully designing stochastic outputs or stochastic methods. But again, on the other hand, if you're perfectly sure this is the ground truth, this is no noise, I agree, right? Then you don't want stochastic output. Does that make sense?
Generally, isn't it possible to pointwise maximum? Just go and find the delta of y such that, your formulation increase.
So these are equivalent, right?
Yes, whatever. In the risk formulation that for the integral, isn't it possible to just select the delta of y such that it minimizes whatever inside that thing is? And then what I mean is, isn't it possible to always find some deterministic rule that minimizes your risk?
So why should that be deterministic?
What I mean is that for any choice you have, there is a deterministic version that also minimizes. That is what I'm saying.
So we haven't. Okay, so it's for a particular formulation, right? So that's the next thing I'll address. The question is, what do we want to minimize? I haven't set up anything yet.
It depends on your cost.
Right.
I agree.
But how do we minimize the cost? So if you let's jump to that. So you're saying what we should be doing is minimize the risk. That's what you're saying, right? So
this is your criteria.
Yeah.
I agree that there might be
Right. But let's say, so let's jump to that, right? So let's say I want to minimize, so I have r delta of theta, right? I want to minimize over delta. Can I do this? First of all, is it feasible to do this?
Just select the delta y such that, you can minimize inside the integral.
What do you need to know for the ones inside the...
You need a distribution.
You don't know this, right? You don't know the theta that actually occurred, right? Of course, if an oracle told you this is what the underlying theta is, you can go ahead and minimize the risk for that particular value of theta. But it's a chicken and egg problem, right? The whole goal is to obtain what theta is, right? So I cannot minimize this, right? So this is impossible. Do you see that? Do you want to share it with the class? In general, I'd prefer that let's have one conversation, so I want people to participate.
Can you try and pick a theta, for that theta find delta that minimizes, and then for that delta find new theta?
Right, so we have to set up the problem, right? But we can't be specifying this as the objective, because this depends on theta. Do you see? I mean, we can worry about solving it later, but first, what should we be solving? We haven't even specified that objective. And you see that we can't solve this problem, because I can't even write down this function, right? Because I don't know theta, so I can't evaluate this, so I don't know this. Do you agree?
Yeah, my question was different. Why wouldn't you just pick theta for that theta minimize the risk? Find the delta. Find the delta that minimizes the risk.
Mm-hmm.
This delta is supposedly going to give you an estimate to new theta.
Right.
That theta would be the closest until you find a good fix for it.
So you're proposing a strategy, right? So you keep searching theta, and then the risk. So the question is, what, in a way, what I guess you're saying is you should also do this. Is that what you're saying? That's my interpretation. Should we be doing that? We'll come to that. Okay, so we have to do something about theta, right? That's for sure. We can't ignore theta and just solve this, right? So that's the first statement. But we can, now I guess the question is, should we do this? How do I handle this theta? That's what will give rise to different formulations. But yeah, I'll come to that in a second. But I think there was somebody else who raised their hand, so I want to make sure. Who was it? Somebody here? No? Yeah.
But in the Bayesian case, it's straightforward that we also take the expectations.
Right. So let's come to that, right? So now let's set it up. Let me erase this because this blocks the way, so you know what this is. So let's now set up what we want for different settings. Right, so for the Bayesian. So what should we do in the Bayesian case? This risk is a function of theta, but what do I know about theta? In the Bayesian setting.
The prior?
The priors, right? So the natural thing to do is average over the prior, right? Because obviously the theta that's more likely, I put more weight there, and theta that's less likely, I put less weight. And so that's called the Bayesian risk, where all I do is take expectation. So this is kind of like my theta as a random variable. I hope that makes sense, right? So this is now just a function of the detector, and you don't have dependence on the theta. Right, so that's a natural thing to do in the Bayesian setting. So what should I do in the frequentist setting? What are some reasonable choices I can make, right? So I'm setting up the objective, so it's up to me to decide. But what are some reasonable choices? Should I be doing this? I mean, first of all, this should be, the two should be exchanged, right? So you can't, you have to first or do some optimization over theta. Sorry, and then you want a detector that satisfies that, right? First, you see the order of optimization, right? You're evaluating risk point-wise for each value of theta. You want some kind of a summary statistic, right? Something that is a function of all of the theta in that set, and then you want a detector that optimizes this measure, right? So you're computing some kind of inner measure here, and then you minimize that detector that satisfies, that minimizes that measure. The question is, what should this measure be?
I would first compute the worst case scenario.
Right, exactly, right? The maximization. So it shouldn't be min, it should be max. Why should it be the max?
Well, it's a game between theta and delta. So you want theta to choose the worst case possible, and then you want to minimize the worst case.
I mean, that's a modeling choice you're making, right? Because you don't know, theta could be any of these possibilities. Even in the worst case, you don't pay a lot of, huge price, right? So here, you're designing for the worst case when you do the max. If you did the min, what would you be doing? Yeah, exactly. It's the best case, right? So you're lucky you get that best case theta, you have a very good detector. You're unlucky, then you may have very bad performance. Right? So many times we design for the worst case, and that's also called robust detector, right? Because the idea is, I may have different possibilities. No matter what, I'm protected, right? I have at least this level of performance, and that's the best possible one, right? So the robust one is minimizing the detector for the worst case choice of theta. It's called robust detection. Right? So in the sense, for the Bayesian one, it's min over the average. We can do the average because we have a prior, right? Whereas in the frequentist setting, we have no prior. So what we can do is look at the worst case. What are the other possible choices? Can we do something else? Let's think again that example of binary detection, right? So, and let's pick that example of a nuclear plant. I'm not a doomsday person, but let's kind of go with that example, right? So let's say most of the time the plant is functioning okay, right? But if there is anything that's anomalous or problematic, you have to have an alarm go up, right? You have to notify the personnel that something's wrong, right? So, if something was truly problematic in the plant, I mean, this can be catastrophic, right? So there are human lives at stake. So in this setup, you don't want to miss if there is any problems with the plant, right? But then on the other hand, you could just always keep alarming. You could always say this is, there's something wrong, right? But then in that case, it's not useful. People won't even ever trust the system because then, you're just alarming all the time. And we see that with our fire safety drills. Right? I don't know if you're like me, I'm just like, okay, I'm staying in my room. So that's also something you have to really think about designing these systems when it's for human consumption, because if you're just sending out alarms all the time, people no longer have any trust in the system. On the other hand, if you don't send enough alarms, there could be some catastrophic situations where there's safety risks, there's implications on human life, right? So for those kind of setups, you want to balance between the two kinds of errors, right? So there is one error which is, there is truly a fire and you miss it, right? So that's one kind of error. The other error is the false alarm, where you have no fire, but it falsely said that there was a fire, right? The two errors are very different, right? They have very different implications in the real world. And so we can't just treat them as an average, right? We can't even treat it as a worst case because the two are not the same. I want to put unequal weight on the two, right? And you can't sometimes do it as a Bayesian setup because you really don't know the prior. I mean, what is the prior of a fire getting caused? That's maybe very hard to compute, right? So to get around that, the formulation that's used is called Neiman-Pearson. And what that sets it up is a constrained optimization problem, right? So what it says is, if there is a fire, I want to maximize the probability of detecting the fire, right? So I'm maximizing the, so here we won't deal with the risk because we're directly thinking about probabilities, right? So there is the probability of detection. Let's say that the underlying hypothesis was the alternate hypothesis. And then my output correctly detects that it's the alternate hypothesis, right? So think of it as, right, the fire actually happened and then you detected the fire. This is a good scenario, right? So you want this to happen. So this is known as detection probability, or I'll use the notation PD in general for this. And this is called detection probability because you're detecting the event of interest. Okay, so we want this to be as large as possible. Right, so if there is a fire or a nuclear catastrophe, we should be detecting this. But then what is the constraint? The constraint was the false alarm that I described. Right, so on the other hand, let's say there was no fire, right? So there was no bad event that happened, but still my detector ended up saying that it happened. Right, so this is the error that's made that says that even though it was the null hypothesis, that is there's no fire, it thinks there is a fire. And we call this the false alarm. So what should my goal be with respect to PD and PF?
Well, high PD and low PF.
Exactly, right? So it's that trade-off between the two. And in many cases, right, we typically can specify what PF should be, right? And that may be based on like kind of how much humans tolerate a false alarm, right? So maybe, we have a fire drill once a year, maybe it's okay, right? So, I mean, in that case, it's planned, it's not a random error, but, or a false alarm like that, a few times a year, I'm okay, but not too many, right? So we'll specify this as a constrained optimization where I say that the false alarm should be less than some value. And then subject to that, I want to maximize the detection probability. Right, so of course the PD is, this is a function of theta 1, PF is a function of theta 0 in the simple hypothesis case. So here you have this also as functions of this. But we can do the notation clearly in a minute, but I want you to understand the intuition.
So may I ask you a question not related to this one, to the previous one? So I'm still confused about it. For both of those scenarios, the first one, the second one.
You mean the robust and the Neiman-Pearson? Yeah.
Whatever I think that is, you can find some deterministic rule because this is some convex going over. What I mean is there is some deterministic rule that can solve it. So is there any scenario that the stochastic rule does make sense? You can find some deterministic rule that gives something.
That'll be the rest of my lecture. So we'll go into the details of this. We'll exactly address that, but let me go through the derivation. But yeah, that's what we'll address. That's a great point.
It seems in limit prison there is no risk involved. Right? We can do the same thing by defining a cost that has higher cost for type 1 error.
Right. You can always kind of also scale it with a cost, right? But the idea is, you can always translate that to also just a probability, right? So because it's just a scaling, right? So that doesn't kind of buy you much. That's why it's convenient to just directly think in terms of probabilities.
For binary case, I can see, but if you have, for example, 3 cases,
yeah.
You can have lots of combinations.
Right. So and again, that's why beyond binary, the theory is not as fully developed, right? Indeed, there may be, it depends on the setup, right? Like you as a plant designer should decide what should be the specification, but a common one that's used is, right, if there are multiple, there's only usually one alternate hypothesis, so one bad event, right? So typically that's the case, and then lots of other baseline, null events, right, that are not problematic. So you control false alarms for all the null events, and you maximize the detection of the alternative. Yeah, but you need this kind of, it's still in a way binary because you're saying there's one problematic event, then there's the rest of, right, no events that are not to be, where the alarm doesn't matter. But I agree. Yeah, so in general, you could have all kinds of combinations, right? Maybe, some are less catastrophic, but still dangerous, right? So you could have all these gradations, and it gets complicated, right?
This is a modular choice to set.
Yes.
There's some systems that there's no some.
And I think that's the comment I also made in the beginning of the class, right? So I talked about this modeling choice, but also your objective, right, is a modeling choice. And I know, unfortunately, in these courses, we don't spend a lot of time on this, which is many times that's the most important thing in practice, right? But then again, it's hard to cast it as science because it's so scenario dependent. For instance, one example of bad design was the Uber accident, the fatal accident that happened in Arizona. I don't know how many of you recall news reports about that. This was at night, the person who was the human driver was distracted, I think they were seeing some video on their phone, and this pedestrian came across the street, right? And in this case, the LiDAR detected it. Right? So the sensor was not the problem. The sensor actually got the detection right. But then it's the algorithm after that, right? So once you see the raw observations from the sensor, you're making this choice. Should I really raise an alarm or not? Should I raise the alarm to the human? And the choice that was made there was to calibrate, kind of like this trade-off was wrong. Right, because, and there was also an underlying reason for that because, at that point, there was, and even today, it's hard to, you may get a lot of false alarms because there's lots of bumps on the road, all kinds of, noise introduced, so it's still challenging to come up with a robust detection of objects, right? And now it's a combination of LiDAR and computer vision and all kinds of other modalities, but it's still challenging to do this trade-off, right? But there was a design choice made, right? There was implicitly or explicitly a decision made that, okay, I can tolerate false alarms only to some extent, so I will give up on detection probability. So in any practical application, we are always making this choice between how to balance the two. And that's not an easy one. Any questions here? So is the setup clear? Right, so the Bayesian risk, we look at the expected risk with respect to the prior, right? We just average over the prior. The robust one, we look at the worst case. No matter what is the choice of theta, what's the best detection I can get, right? In the worst case. So you're playing the game between the two. The Neiman-Pearson, it's designed for catastrophic events. So typically there is one catastrophic event and then there are all the other null events. In the binary case, there's one alternative and one null event. And you limit the false alarm of the null event and you maximize the detection of the catastrophic or the alternate hypothesis. Right, so those are the setups. We haven't yet found the solution, but we've set up these optimization problems. Any questions here? Yeah, so now we can get to solving these problems. I guess I can erase this, right? So I'm just worried about utilizing that corner. I worry people here may be not able to see it, so I'll just. So yeah, the Bayesian one, I know there were already thoughts about what the optimal detector should be, right? So let's kind of go through that somewhat quickly because the other one requires more time. So for the Bayesian one, so let's take the special case first. If you recall, the special case is this, the error, you just have equal cost of error for all kinds of errors, right? So, and in the case of Bayesian one, that's nothing but the maximum a posteriori detector or map detector. Right, so intuitively what you should do in the Bayesian case is look at the posterior distribution. Right, the posterior is the distribution of theta given your observed data. Right, so this is my posterior. And then I want to maximize this probability. Right, I see. Want to see where the peak of this distribution is, right? And I want to, in this case, recall that theta only has discrete set of choices. So you can just write it down as, what you look at the probability of theta taking each of the I values, and you look at the one that is maximizing this probability. And you can do argmax, right? So that is my detection. And that is a special case of that cost function, right? So here we've looked at like equal costs for all the errors. And this is intuitive, right? Like there is the posterior distribution in general, right? That kind of could have all this, kind of shape for the distribution, but then you just look at what is the most likely one, right? I mean, of course, I wrote a continuous distribution here. Of course, you can do the same with discrete distributions. I mean, this is a natural choice for detection in Bayesian setting. Is that clear? You want to look at the realization that maximizes the posterior distribution. Right, so once we agree on this, right, so this you can now use the Bayes rule. So when I do the Bayes rule, how can I further simplify this? What is the denominator in this Bayes rule?
A constant.
Right, it has nothing to do with theta, right? I mean, it is a distribution of y, but it marginalized out theta. So it's the same as just optimizing the numerator, right, which was the joint distribution. And that is nothing but the prior times, right, the model. So you want to do like the argmax of this. And this is in,
Steve, even for the first part, what if, for example, that probability is large, but around it quickly the probability is small. So it makes sense to consider probably some interval.
So this is discrete, right? We are doing the detection. We'll come to estimation later on in the later class. Yeah, so estimation, that's why is right? And this is a choice we made, right? Indeed, in some cases, maybe that's not a robust choice. It's a good point. But yeah, keep it in mind for a later class. Okay, so this is now just a discrete set of choices, right? So, and in fact, in the binary case, there's only 2 choices, right? So I want to like look at the prior distribution under the null I won't call it null in the Bayesian setting, under theta 0, right? And then under theta 1, sorry. Right, so if theta 1 is larger, I should like say my detection is 1, right? On the other hand, if this product is larger, I should say that my detector should output theta 0. And what do you see this connection to? Right? This is the same as the likelihood ratio test. And so looking back here, you can see, it's also the sufficient statistic. We could go from that angle, or we could like kind of see that when we look at the optimization function. Right? So the likelihood ratio, right? The threshold here is nothing but what? Pi naught by pi 1, right? So the ratio of the 2 priors. So what are some intuitions here? Let's say that pi naught is very high and pi 1 is small, so the ratio is large. So meaning theta naught is very likely and theta 1 is not likely. In that case, how does this threshold change? This gets larger, right? So naturally this ratio. And what is the intuition? Like, if like you have more likelihood for theta not appearing, then you should make this threshold very high. So there's much higher bar for the observed data, right? The likelihood of the observed data for you to declare it's theta 1. So in a way, you're reweighting based on your priors, right? And that's what Bayesian approach is. You're taking into account a combination of your prior as well as your observed data, right? It's this combination. And so you see that naturally happen here. You're looking at the trade-off between the two. Okay, so I won't do the example here, but it's there in the class notes where if we write this down for the Gaussian distribution, you can look at the trade-off between the variance and the priors, right? So let's say both under theta naught and theta 1, they're Gaussian distribution, right? So let's say I have theta naught sigma square, I have theta 1 sigma square. So the mean is different, and you have some prior over the mean. And then you also have the variance. So I won't write down the exact, form here, but what do you think intuitively is the trade-off between the variance and the priors? So let's look at the extreme regime, right? So let's say the variance is very large. I have this Gaussian distribution extremely spread. What will I rely on more? Will I rely more on priors? Will I rely more on my data? What does your intuition tell you? You have a very large spread of your data. The variance is high.
Oh, this is not the prior distribution.
This is the observed distribution. Sorry, this is f of by theta naught. So this is our observed distribution, right? So your observed distribution is like either my mean is here, let's say, or my mean is here. And both have the same variance. For simplicity, I've chosen the same variance. And now my observed distribution keeps having larger and larger spread. What should I trust more? The prior or my data? Prior, right?
So you're saying that like the spread of the data is just becoming larger and larger. Like the observed distribution is based on the data, and it's just becoming larger
right? It's a normal distribution, yeah.
So it's just like kind of getting very fat.
Yeah, it's having more and more variance, right? So indeed, more and more randomness.
So it kind of doesn't really, so it says less and less.
Yeah.
In some ways, okay.
And that's intuitive, right? So if you're saying this is my mean, but you could have all this variance, it's very large. You don't know where the mean is, but you have the prior to go by in the Bayesian setting. You should go by the prior, right? So in the limit, only the prior matters, right? You completely ignore your data. And you can actually see that in the expression. I'm not writing it down here, but it's in the notes, so I encourage you to go do that derivation. It shows up in this kind of computation.
In these settings, the priority means the probability for each hypothesis is equal.
Need not be. I haven't specified, right? I haven't specified anything about the prior distribution. It could be arbitrary. All I've plotted here is the model, right? So I haven't done anything. I've said there is some prior, and I tell you what the prior is. The question is one of reliance between the prior versus the data. What should you rely more on? Or in the sense, the optimal detector, what would it put more weight on? Right? And intuitively, it's if your data has a huge spread, you should rely on the priors. And you actually see that come up when you do the derivation of the likelihood ratio detector.
So that means I have almost no observation of my data. So the variance is...
Yeah, it's kind of, your data is very noisy, right? It's not telling you much useful information about theta. Right, and then you you rely on your priors because of that. Okay, so that's an intuitive statement I wanted to make, right? So, any questions here? Right, as an exercise, I encourage you to go through that derivation. Okay, so this was binary hypothesis. Let's do the general Emery hypothesis, general costs in the Bayesian setup, right? So I want to minimize this Bayesian risk, which is the average. And sorry, remind me your name?
Sorry, Hamid.
Yeah, Hamid was, like pointing this out, whether that should be deterministic or not, right? So that's what we will address now, and we'll do it in the general case. So in the general case, let's say I have K hypothesis. Right, so even going in the binary, you kind of saw that, right? So okay, before we even go to the K hypothesis, in this setting here, is there anything you gain by using a stochastic detector? I mean, this one we made it deterministic. Is there anything you gain here? Actually, that question is not that well posed, right? Because I came up with this as the objective. So by definition, I'm only outputting, whatever is the optimal value. But if I write it in terms of the cost function, you will see that. So never mind. You will see that in the general case, and it's also true for the binary, but let's just jump to that. So the general, we'll do the Bayesian risk again. So this Bayesian risk was nothing but expectation of the cost function, and the expectation was both over the detector as well as your theta, right? Both are random variables here. You're taking expectation with respect to both your detector depends on your data, and the cost function that also, and the theta that depends on the prior, right? That has a prior. So this is the expectation. So for just simplicity, I'll write it down. There's only K possibilities, right? So I have K hypothesis. Let's say this is from little k equals 0 to k minus 1. So these are my K possibilities of hypothesis. And so there is some cost for each of the hypotheses. And then let's say my detector outputs k as the hypothesis, right? So this is my average cost, right? And I've also averaged this, I can also, you have the prior, the ck can be also averaged over the prior, right? So there's some average cost under each hypothesis, and then there is the detector deciding whether it should output that hypothesis. So I can set this problem of minimizing the risk as, okay, so I minimize this quantity. Let me just write it again. What are my constraints? So this delta k of y is nothing but, what is it? It's the probability I'm outputting k conditioned on my data, right? So this delta k, remember this was the general probabilistic detector, right? We have it here, but I will write it here again. So it's also a function of, right? I can write down, this, right, like the Bayesian risk, of course, as averaging over theta, all this, I've hidden it through these quantities. At the end of the day, you can write it as average over all the hypotheses. But then you also have the detector making those choices, right, which hypothesis it picks given the data. Right, so the detector is picking a certain hypothesis, there's a cost associated to that hypothesis, and it's the average. Right, so I've hidden all the details of that, but that's what the Bayesian risk minimization reduces to in the k-ary hypothesis. But what is the constraint on my theta, right? So I want to minimize this over, delta, again. So I want to minimize this over delta. Obviously, I want a good detector. But what constraints do I have on my delta? What is delta here?
0, 1.
Right, it has to be between 0, 1. And then what else? So each delta k, right, is between 0 and 1. What else? They should sum up to 1, right? What do we call this object? If you look at all possible vectors that take this, that satisfy these constraints, what do we call that? Right, it's also a special convex body, right? It's a simplex, right? It's a probability simplex, right? So also generally we have this notation, right? So it's usually delta of k minus 1 for k hypothesis or k realization. So this is the probability simplex. Okay, so let me rewrite it here to make sure So how many here have done a linear programming course or done linear programming? Do you recognize this problem? What is this problem? Right, forget about the details of estimation here. Just let's look at the problem, right? So this summation, I'll just write it as inner product just for shorthand. Right, so this vector c is nothing but I'm like looking at all the costs for all the k hypotheses. And same for delta, right? All the values of delta, I'm writing it as a vector. Okay? And so this summation is nothing but an inner product, right? So just for compactness, I'm writing this way. So I want to minimize over delta, but delta should lie in this probability simplex. Okay, so I'm just writing the same thing compactly there. So take a moment to convince yourself it's the same thing.
Why still we have the dependence on y? Shouldn't we take the expectation respect?
Yeah, sorry, there is no y. Thank you. So, I mean, there is, right, so there is another outside expectation, right? So there will be, one more expectation, but that should not affect, right, so there is, let me see what is the cleanest way to make this. I mean, you can't ignore y, but on the other hand, there should be a simple way to. Sorry, this is now, so I didn't write down the details of it, right? So this is still a function of y. So think of it as r of delta conditioned on y, right? These two are not equal. So this is what we wanted, right? The average, but I can still now take the average over y, right? That doesn't affect this optimization. There's just another outside averaging. Do you see this? I can always take the optimization inside, right? There is an integration over theta and there's an integration over y. And we've just taken the optimization inside, right? So the outside integration over y, I can do it and it doesn't affect this. Okay, so good point. So there is dependence on y. Okay, so this delta, all this is dependent on y, right? So I'm kind of. So do any of you recognize this problem? Okay, let's not go just by recognition. Let's go by, trying to come up with intuitively what's happening, right? So this is my attempt to draw the probability simplex. Right? Over 3 variables, 3 hypotheses. What is this here? If I set this to be some constant value, what do we call this object? Let's say gamma. It's a hyperplane, right? So there is now this kind of hyperplane and you're moving the hyperplane depending on gamma. You can kind of. So what do you think should be the optimal value here? One of the vertices, right? I mean, this is simplex programming. Right, so you'll study, more generally in linear programming that in these cases, right, it will be one of the vertices that'll be the optimal point. And what I'm trying to convey through this figure is, first you kind of have to go through the vertex and then kind of go to the interior, right? So the minimum value will be one of the vertex. When the hyperplane is intersecting the simplex, it has to first go through the vertex. Okay, and that's why, what's the conclusion? Right? What does the vertex correspond to? Anybody else? What is the vertex here? What is the vertex of a simplex? Right, because it's 1 and then 0 everywhere else, right? That's what the vertices are, right? Similarly, 0, in this case 0, 0, 1, right? So so those are the vertices. So it comes from the linear programming fact and also intuitively that you have to go through the vertex first, and that's why the vertex is the optimal point here. So the conclusion is, for Bayesian detection, the optimal thing to do is just deterministic, right? Which again was your intuition, okay, why do we need randomness? In the Bayesian case, you don't. Right, the deterministic is the best thing you can do, and there it's also preferable due to other reasons to be deterministic. Okay? Great. By the way, is that like clock not on time? Is it exact? I didn't get my watch. What?